Yes, so I do data storytelling as one of the things that I try and both do and teach, but I also teach data visualization or data in the context of data science or in context of exploring data. And one of the questions that I would typically see is, or come across is, how do I move beyond just simple visualizations and try to visualize multidimensional data, right? So that's kind of the reason for why I kind of made this talk, and I've been trying to give this talk to kind of educate or also, kind of inspire people to learn about this much more, right? So I'm going to begin with just a little, probably go back to 1800 to this book called Flatland and begin with this story. So Flatland is a book, a very nice book anyone wants to read, a romance in many dimensions. It's by Edwin Abbott in literally the end of the 18th century, or 1884. And the book is really an allegory for the Victorian time, but it also uses all these characters which are living in this two-dimensional space, and they are literally either a line, a square, a triangle, or a hexagon, or different polygons. And the protagonist is this player who is literally a square, right? And the square, if you are living on a two-dimensional space, is nothing but a line, right? So if you're looking at someone who's a square in a two-dimensional, it's literally a line. And the story really kicks into gears when the square is visited by a sphere. And a sphere is a three-dimensional figure. In a two-dimensional line, he can go in and out. He can become a circle, or he can literally disappear, because that's how the square sees this two-dimensional object or three-dimensional object projected on a two-dimensional space. And no matter what the sphere will tell him about that there is a third dimension, he's not able to understand it, because he's captured, or he lives in that two-dimensional space, right? So ultimately, the sphere has no other way but to pull the square out and show him that he's actually a cube who is just a square in a two-dimensional space, right? So a lovely book. Anybody wants to read, please go and read The Flatland. But in order to show, and I'm going to kind of pick up from that book and literally show rather than tell a lot about visualization, because I guess that's the power of visualization. I can really show you a lot more than I have to speak about it. I will speak to kind of tell the story, but I will show more than I'll tell. Okay, so we are using visualization because we are visually wired. More than 50% of our brain is used for visual processing. 70% of our sensors are in the fovea in the eye. And actually, you can pretty much enter or see any scene and get a lay of the land in less than a second, or maybe like 100 milliseconds, right? So we are really visually wired, and that's why we want to use visual abstraction. So if you see a phenomena out there, you have both the options to choose either symbolic abstraction, which is what a lot of us are comfortable with, especially in the data world. But the visual abstraction is just another way of looking at it, right? So visual abstraction can also represent the data as powerfully as a symbolic abstraction. And visualization is nothing but the transformation of the symbolic into the geometric, right? So that's what visualization is. And I'm going to show you what this means, or how to think about this in basically these four contexts. So I'll start with a very small data, move to a slightly larger data, talk a little bit about big data, and then come to wide data visualization, which I guess is kind of the crux of this talk. Feel free to ask me questions in the middle, but I would go at a rapid clip. So let's start with visualizing a very small data. We'll take a very trivial data set, which has just 5 areas, so 5 category variable or categorical variables, and sales or any numbers used to represent sales in that. So there is a numeric data there, right? So very simple. You probably can't think of a simpler data set than this, right? If we were trying to visualize this data set, we would basically acquire the data. So we have the data. We would parse it into variables. So we'll say, OK, there is X, which is now a categorical variable, which is area, and Y, which is sales, and I map that. So I basically acquire the data, parse the variables. And then I encode it into a shape. And let's say we were trying to construct a bar chart. So I encode the Y, which is the sales, into a bar. So the length of the bar is literally showing how long it is. And because I need to map it onto a pixel map of, let's say, 200 by 200, I map X as positions, so I know which positions I want to show them. And I make the bar as a way of according to that size, right? So I basically encode the shapes and select a scale and make it. And then I do one more step, which is I render it in a coordinate system, right? So I basically render it, in this case, with a Cartesian coordinate system, right? This is what we do in visualization. This is the process of visualization, no matter how big or small the data is, right? And this is really powerful, because once you understand this, you can basically create unlimited number of visualizations. So suppose I want to render the same thing, not only as a bar, but as a point, maybe as a line, maybe as a thicker line, which is in this case a bar, or actually change the position also a little bit, so stack the bars or stagger the bars, right? And I will choose a coordinate system. So I'm choosing 5 different kinds of encoding and positions, and I'm choosing different coordinate systems. And if I do that, I can create many visualizations. So I choose a typical X and Y Cartesian coordinate system, and I can get a dot plot, a line chart, a column chart, stacked column, or waterfall, right? I can cheat very quickly and flip the coordinate system, and I can get 5 more, right? So I can get 5 more of those. So a dot plot, again a line chart. Now we have to name them new things. So instead of column, we call them a bar. So now we have a bar chart, a stacked bar, and a cascade, right? I can again choose another coordinate system, which is polar as opposed to coordinate, and say I map X to angle, Y to R, and I come with another 5, which is marked radar, line radar, coxcomb, bullseye, and polar waterfall. And some of them don't have names, because we're now in this territory where we are creating unlimited visualizations. So I have taken the liberty to name them what I felt was appropriate, right? I can again cheat, or not really cheat, but flip the coordinate and map X to R and Y to angle, and get 5 more. So I get now a target, line track, windrows, everybody's favorite pie chart, and a polar cascade, right? So very quickly, with this trivial data set and a little bit of understanding of how to map the data and visualize this, I can create 20. And this is with a very trivial data set. As the data set expands, the number of visualizations that are available to you will also expand astronomically, right? Or exponentially. So what is the database process for a small data? We acquire the data, we parse it into variables, we encode it into a shape, we select a scale on how big those shapes need to be, and then we render it in a coordinate system. So with these 5 steps, if we follow these 5 steps, we can visualize any amount of small data, right? With me? Okay. So this is not new. It's not like I have discovered this suddenly and I'm coming and presenting it. If any of you use these tools like R, Python, or Julia, there is a whole grammar of graphics, which is a book by Leland Wilkinson, which describes kind of this creation of visualizations. And if you don't use R's graphics package, but use something like ggplot, that's based on the grammar of graphic. So is Gadfly package in Julia. Python doesn't really have a pure grammar of graphics, but if you use Bokeh, I guess Bokeh is quite inspired from the grammar of graphic. So those are, these packages are available in some cases, or if you use a UI tool like Tableau, you can also do a little bit of this in a much more graphical way, right? So there are tools available to do this. So that's how you would probably start from a small data, but now we are kind of in a slightly bigger context. So let's move to a larger data to kind of see whether this point still holds, right? So I'm going to visualize another set of data, which is 24,000 pin codes in India. Now, pin codes are, the equivalent would be postal codes. So in the US, you'll call it zip codes. In other places, you still call it like postcodes or whatever the denomination is. But basically, demarcates an area within a geographic space, right? So there are about 24,000 of them. And basically, a pin code like this would have a latitude, a longitude, and you can have a place to identify where that is, right? So this is a slightly larger data set with a very simple data schema of these 4 elements, right? So if I was to visualize it, I can put all of them together as a scatter plot. Effectively, that's what I'm doing. I'm plotting the latitude and longitude on a scaled map. In this case, the coordinate system is a geographic coordinate system. But other than that, I've just done a scatter plot, literally a scatter plot. Now, because there's going to be a lot of plots, I have to play around a little bit with alpha, or what we would say the transparency of the dot, so that when there are more dots, it appears to be darker. When there are less dots, it appears to be more showing the background with color, right? So you can see where it's dark orange, there are probably more postcodes in that region. Where there is light or more black color, there's probably less pin codes, right? So I can very quickly visualize also large data sets, as long as I then start to tweak it a little bit, right? But what if I want to show the geographic nature of the pin codes, right? Pin codes by nature are a little bit geographic. So the first digit in, say, 560076 is really 5 is an area that's marked. So I can then choose other variables in that visualization to show it. So I can add color, and I can say now the first color or the first digit is denoted by a color, and now you can see that there are probably 8 regions in India which are demarcated by this first digit in the pin code, right? So exploration in kind of data set is actually really an iterative process. It's not nearly simply as saying, I want to do it this way. You probably create a visualization, and then you move on to another one, right? So there's an element of refining that you would do. And the refining could be in the form of filtering. It could be in the form of transformations. But there'll be an element of refining that you would do, right? So if you think about the database process, again, database process for a large data is probably you acquire the data, you parse the variable, but then you do some amount of refinement to actually think about how you want to map the data, because the data is not a very trivial data set that you can just choose the chart to show it. So you refine the data, but you then do the same thing. You encode the shape, select the scales, and render the coordinates, right? Let's move on to big data, right? Now, so what's a big data? Let's take a big data. Let's take a million numbers, a million data points, right? And try and plot them. Now, visualization in that way is not really great, because if I take a million data points, I'm in the same order of magnitude as the number of pixels are there in my MacBook, right? So I'm at a million data points, and no amount of alpha treatment can actually make me see those million data points, right? So visualization in that way is not really great. It doesn't scale very well with the number of data points I have, right? So what can I do? If I'm visualizing, I can sample it. So sampling is one possibility. So sampling can be effective as long as I'm kind of doing the right way of sampling. I'm overweighting for unusual values. I can probably get a sample and get a sense of the map, right? I need to be a little careful, but sampling is one way to treat with it, right? Or I can model it, right? So modeling is great because modeling scales very nicely. That's why we all love modeling in big data, because modeling scales nicely. But modeling is what I call first order of understanding, right? I know what I don't know. If I know what I don't know, I can model it. But visualization is really great because it really attacks a second order of ignorance, I would say, which is I don't know what I don't know. Because if I don't know what I don't know, I can't really model it. I really don't know anything, right? So I have to visualize it so that I get to form some hypotheses about the data. And that's why we're trying to do visualization, especially in the exploration part of the stage. So if I can't do data, I can't map the whole data, I can't sample it, I cannot model it, then maybe their option is to bin it, right? So binning inherently is a way of aggregating the data in some ways, or in this case, 2D bins, to actually start to solve a lot of these challenges, right? So binning is one way to do this, and there are a couple of good papers if anybody wants to read. Bin Summarized Smooth by Hadley Vikram, who basically takes a MacBook Air or a MacBook Pro with 16 GB of RAM and basically visualizes 100 million data points, right? Or even Jeffrey, his team has this paper called IMEMS, which is real-time visual querying of big data, and they look at how binning in a very interactive way could actually do that, right? So those two are really good. And binning is not really new. One of the first things you probably learned, if you're in grade 5, is here are a set of kids that have come to your birthday, or people who have come to your birthday party. Can you bucket them into these age groups and then draw this as a map? This is probably a grade 5 Khan Academy exercise, right? And binning is really great, and that's what histograms are, right? So the first visualization you learn is not really a bar chart, is not really a pie chart, is really a histograms. But what happens is, because of the tools that you use, you kind of forget this. Because histogram is not a default that is there in Excel, nobody has probably used it as much. So we rely on the charting library. So tools impact us in a way which could be actually negative for us, right? But histograms is really the way to go if you're looking at big data. And Amanda Cox, who is the New York Times graphic editor, says maybe calling 2015 the year of the histograms, right? Now, conferences are a good time to come up with quotes, so I thought I should also come up with a quote of my own. So I thought, here you go. Visualizing big data is the process of creating generalized histograms, right? So here is a quote that I thought this is a good environment to do that, right? But in terms of the process, what have we done? We've taken the same process of acquiring the data, parsing the variables, filtering the data, aggregating it in some way. And that's kind of the step where you add it here, encoding into shapes, selecting the scales, and rendering the coordinates, right? So the process is still the same, but we have an aggregation step in the middle. And a lot of tools that are being designed right now, or let's say columnar architectures, they're all trying to do, can I do pre-compute some of these aggregates? How can I make this faster, right? How can I design systems which allow me to access some of these aggregates very faster so that then I can actually visualize them faster? So the kind of the engineering challenge of big data or storing it or accessing it tries to target this in a very smart way, target the aggregating part, so that then I can visualize it much faster, right, or access. Okay, this is as much as I would go on big data visualization. So let's go to wide data, right? So big data is just the number of observations are really large, right? But what if the number of columns in my data are really large? So that's really wide data what we're talking about, right? So in wide data, we're going to talk about a little bit of these approaches, right? So there are many ways to tackle these approaches. You can start with very standard 2D, 3D mappings. You can use glyphs. You can then start to do transforms, or you can then use stacks or pixel-based approach to actually do it. So the way to think about this chart or this is that the need for interaction goes more as you move further to the right in each of these options. And the ease of interpretability in the sense that whether you can understand what the visualization is also decreases. So it's easier to understand what's on the left, harder to understand on the right, right? So again, what if you were doing a visualization for communication, you'll stick more to the left end. If you're trying to do a visualization for exploration, or even maybe a dashboard, or something that a scientist would be repeatedly looking at and can learn the process, you may end up going much more to the right, right? So we'll again, in the essence of trying to show rather than tell, I'll show you kind of move across this spectrum and show you how to think about visualization. So I'm going to use a very common data set. If anybody uses R, it's called the diamonds data set. It comes with a ggplot, and it's about 50,000 data points. So it's a large data, not a big data. So it's 50,000 observations, but it has 10 dimensions. So we can at least go up to 10 dimensions to see how we could look at a 10-dimensional visualization. And for those who don't know about the data set, it's basically a price of a diamond. And if anybody's gone to buy a diamond, the price of a diamond depends on the 4 C's. So the 4 C's are carat, which is kind of like the weight of the diamond, so which is about 1/5 of a gram. Cut, so how well it is cut. What is the color of the diamond? And how well is the clarity? So is it got some small inclusions in it, or is it internally flawless, right? So each of these variables, price and carat, are numeric variables. Cut, color, and clarity are categorical variable, right? Now also the diamond also has a shape and a size. So there are other 5 more variables which kind of define the x, y, and z. And because it's not a perfect square, also a little bit of the depth and the taper in the bottom. Not really important to understand everything in here, but these are the 10 variables. These 5 are all numeric, right? So we have about 7 numeric variables and 3 categorical variables. Okay, so let's start. This is how kind of the first 6 rows would look like if you were to look at the table of data, right, of the diamonds data set. Okay? So let's start. Let's start with 1D and 2D. Now, I won't go into this because we're talking about multidimensional and we really want to go to 3, but I will just kind of indicate what it would look like for 1 and 2 dimensional. So you can have 1-dimensional quantitative data, 1-dimensional categorical data, or the combinations of 2, right? So in 2-dimensional, you can have 1 quantitative, 1 categorical, or both categorical or both quantitative data, right? So you have these 5 combinations. And like we said, we could encode it in different ways. You could encode it as a point. You could encode it as a bar. You could encode it as a line. And you could encode it as an area, right? And if you were to do that, you would get these plots, which are many of that you may be very familiar with. So a bar chart or a box plot or a frequency polygon. Some of them may be slightly new, mosaic plots or table lengths or slope graphs. But to a large extent, I mean, these would be the choices you would make. Not the unlimited choices, kind of the considerate choices, trying to understand what is the best way to visualize and understand the data, right? But we really want to go into wide dimensional data, right? So let's go to 3 dimensions. So let's start with 2 and then move to 3 and see how we could do it. So a 2D at the most common level that a lot of data science or a lot of people would use is just a 2D scatter, right? So I'm going to plot price on one axis, carat on the other axis. So what's the price of the diamond? What's the weight of the diamond on the y-axis? And as you can see, there is definitely a relationship that as the diamond becomes big, the price goes up. Not linearly, but it does go up, right? So one of the first things I would do in a 2D scatter is really look at interaction and annotation. So I want to look at, are there some outliers? And yes, there look to be 3 outliers here, which I've highlighted. OK, so you probably want to, so I'm going to talk a little bit about interaction required to do in each one of them, because that also plays a part in visualizing multidimensional data, right? What if you are looking at it very nice, as a data scientist, you would transform the data and you say, OK, let me make it on a log curve on the left side, a log curve on the y side. And once you log it, you can see, OK, there is pretty much a linear relationship that's going there, right? So there is a 2D scatter. So this is the base. Let's take this as a base and move on, right? So you may want to focus it. So the other interaction layer that you would want to add on it is, can I kind of zoom in and filter on it? So if this is my area of interest, carat greater than 1, price greater than 1,000, I zoom in and I can see further. So there is an interaction level of pan and zoom that's also important, right? OK, so that's 2D. Let's go 3. So what's the first option I have to do 3D? If I want to add a third dimension on it, I would basically use aesthetics to start with, right? So I would basically change the size of the dot, change the color, or change the shape. So let me use a proxy of size, like say log of x, y, and z. So like literally saying how big the diamond is. And if I were to use that as a third dimension and say the smaller circles are on the bottom, the larger circles are on the top, that makes sense because the diamond is heavier. It's probably also slightly bigger. And I can start to see that gradation in this. This is about 50,000 points plotted on it. Or I could use color. So in this case, I'm using color to literally show color. And when I do that, I can clearly start to see the stratification, in which case the colors on the D side or the bottom side are not so great. The colors on the top are better. And I can start to see some lines there. And I start to say, OK, maybe there is a relationship between color, right? So I'm now moved to 3 dimensions. I have 3 dimensions plotted on it. And I can start to see some trends in it. Shapes, unfortunately, don't scale that well, right? And this is just 5% of the data. But if I use different shapes to plot, they very easily becomes hard to kind of decipher which shape is what, right? So shape is really not good. Size and color is probably the 2 best bets that you have to do it, right? But we are talking third dimensions, right? If you're talking about third dimension, one of the options is literally to draw a third dimension as you would draw on a paper, right? So we could actually literally draw third dimension going into the paper, or what I would call depth perspective, right? And this is great as kind of if you were doing an isometric engineering drawing, but it's not really great for visualization because I can't really see it very well. So third dimensional as a depth perspective doesn't really work. The only place where it'll work is if your tool allows you to do some interaction with it. So if I can rotate it around or move it around, or I can see it from different dimensions, then a third dimension perspective showing as x, y, and z in these 3 dimensions could probably work, right? So we're at 3 now. How do we go more? How do we go from 3 to, say, 4 to 6? Right? With me? OK. So 4 is obviously the easiest way to start is we can combine size and color, right? So if I combine color and size, as I was doing before, now I have 4 dimensions, or 4 of those variables plotted there, right? So 4 is easy. And how can you do 5? If you had time as a third dimension, and anybody seen Hans Rosling present his data, he literally presents 5 dimensions in the sense of the x, y-axis, the color, size of the bubble, and literally time as the 5th dimension because you're literally showing different views of the data as you move across, right? So if I had time as an axis, I could actually literally move across, right? Unfortunately, I don't have time in my data point, in my data set. So what I could do is literally facet it. So or what we would say create small multiples or create small charts and start to stack them together. The moment I do that, then I have now got 5 charts or 5 different variables plotted in it, right? And why stop at only 1 faceting? Why not do it as 2, right? So I can actually create a whole grid of multiples. And this technique called trellising or faceting or creating small multiples in kind of the design language is a very good way of actually doing static graphs in which you have added now up to 6 dimensions, and you can actually start to see the trends very quickly, right? So this is one of the easiest way to do it, right? Another way to think about this, another way to represent, or people may have seen, is kind of like scatter plot matrices or sploms, which are also trying to do something like this. Or subplots, kind of reversing it and saying, can I map the distribution on an x and y, right? So binned plot or subplot, right? Those are, again, ways to kind of trying to get more variables to map, again, in the domain of about 4 to 6 variables that I can actually do that. Okay? But to really go beyond 4 or 5, I have this constraint of space, right? Even though we have bigger and bigger memory, we have bigger and bigger processing powers, the physical space that I have is actually a very hard constraint. I cannot literally move beyond the screen. I can probably get a 30-inch monitor or a 50-inch monitor, but probably has the same number of pixels in it, right? So how do I break this constraint of a screen? And it's very hard to do it even with creating these small multiples, right? One of the real ways to actually do that is actually create multiple charts that allow me to look at data in a very different way, and then allow me to actually link them together. So I can select a part of the chart, and in this case, the part of the chart, let's say, is highlighted by red, and I can see where those chart occurs in every other place. That's really the way to actually go beyond solving this problem of trying to plot everything in a universal or a single graph, to actually creating many charts which are all linked together. And that's why interaction effects like panning, zooming, brushing, and linking are very important to actually visualize the data. Because here, I can start to correlate the trends from one graph to another, right? And the moment you can do that, you've actually allows you to do as many dimensions as you can fit into that space, right? So you can go beyond that. But easy to do at least 5, 6 in this way. Unfortunately, a lot of the tools that we typically use, at least as a data scientist, don't allow us to do it very well. Some of the BI tools probably do a better job in it than kind of the RStudio if you're using for R, or if you're using kind of a notebook type environment to do a lot of your analysis, because you're very constrained by the space they are, and the interactivity is like built into much more linear narrative fashion rather than allowing you to do multiple views, which would have been a good way to do that, right? Okay, so there is a limitation of tools, but there are some tools which are better at it, especially the BI side, or some of the new ones that are being developed to kind of build interactive visualization from the startup. They do a much better job than just these static tools that we typically use. Okay, so how do we go beyond 6? How do we go from where we were to like 6 and more, right? So one of the options is to use glyph-based or icon-based, right? So instead of just choosing a circle or a dot, can I change that into a different object? So that glyph literally can show me as a star or a stick, or in some cases even churn out, different dimensions. So right, this star, for example, is showing 6 dimensions already, right? So I could take a glyph, in which case this is kind of like a pie glyph, color, cut, table, depth, clarity, and you can see how each of that 50 data points would look in the glyph, right? So each of the data point is representing different elements. And I could map this on go back to my price and price and caret and map it, and now I have 7 dimensions on this, right? Again, it doesn't scale very nicely, but there is one option to actually start to do that. So glyphs are one way to do many more dimensions on a chart rather than just restricting ourselves to a color or size, right? And the other way to do it is to break the Cartesian coordinate system. So because the Cartesian coordinate system is great, but it takes up a lot of space, right? So the only way to do is, instead of thinking of them as orthogonal, why don't I think of them as parallel lines? And once I start to break that constraint and I draw a parallel line, I can literally do as many lines as I can fit. So I can do all 10 of them in one chart. So I can do a parallel coordinate in which I've actually plotted all the variables, all 10 of them on the line, and each observation is joined across with this blue line, right? And wherever there are more blue lines, that means basically more points are being shown there, right? Actually, so this parallel coordinate is one way to do it. Obviously, it has some constraints. So you can see the relationships between price and caret more clearly, so the first two, rather than between price and, let's say, the last variable, which is table, right? So there has to be some element of interactivity built into it to actually be able to do this very well, right? And that's why interactivity in terms of selecting them or moving these axes is really key, because once you get that, you can actually do interaction, and you can start to see these patterns and try and understand. So this is like 10 dimensions, and you can see it in one chart. Now we're using lines to connect it. We could do it other ways. We could bin it in a traditional way and sort it. And you could also do it like a table plot, which is instead of using lines, now I'm using bins, and I'm showing them as bars in my chart, right? So again, I'm showing all 10 of them. But in this case, I'm using kind of like a histogram. So going back to our big data, trying to bin it and showing them all, and I can start to see these interactions, right? So that table sort is another way to think about it. Again, all of these tools, as we go more to the right, and I won't go much deeper, require a lot of zooming, sorting, interaction for it to be working, right? So stacked, again, I could take all the 3 plots and plot it in a stacked way. That's an interaction approach to do it. And the last two are really looking at geometric transformation, which are like coordinate systems. So I could plot it in a star coordinate system instead of plotting it as 1 axis or 3 axes. I'm plotting 5 axes in this case. Or I do projections, which are basically project the data on a 2D space and allow me to move them, which is something called tours and projections, which again allow me to actually look at this, right? The last approach, which is really harder to understand, is really take each pixel and represent the data point as a pixel in it. And it's called pixel-based approach. You can use spiral pixel curves or pixel bar charts. They take a much longer to understand. But they can be good in situations where you're doing something that people are repeatedly looking at and can build some literacy around how to use these graphs, right? The challenge with, obviously, the more elements to the right is that it's harder to use them. Right? So data which processed for white data is basically we still acquire the data, parse the data, filter it, aggregate it, encode the shape, select scales, but we then also render it in some algorithms. We also make some views, and we also add interactivity to it, right? The message I want you to take away is when you're trying to do wide data visualization is to encode wisely. So think about what variables you're encoding and how you are encoding them. Use the space and multiples as much as you can. Add interactivity, so really look out for tools or see how you can add interactivity to tools. And in extreme cases, because we still only got until 10, if you have to really do more dimensions, you have to look at algorithms which reduce the dimension and allow you to do it, right? So those are the 4 kind of things I would urge you to look at. All the code in this slides is available on GitHub, how to create each one of these. This is largely done in R. All these are the R packages that were used to create a lot of these charts. You can go and feel free to fork it, build on it, learn how to do this, and use it. I'm just going to end with one last quote. The greatest value of picture is when it forces us to notice what we never expected to see. Right? So if there's one message I want you to take back from is to use visualization before you start doing your modeling, to start to see what may be there that you have missed out, to use visualization as a way to increase your understanding, to increase your hypothesis about the data, to do feature engineering, to do whatever you want to do after that in terms of modeling, not just as a communication made, right? So think of breaking that constraint of just going straight to modeling, but use visualization along with it to really improve your, right? This is, so my name is Amit Kapoor. I work in this intersection of crafting visual stories with data. So in the intersection of data, stories, and visuals, these are my 2 websites, amitcaps.com, narrativeviz.com. Follow me on Twitter at amitcaps. I will be tweeting out the slide deck for this, and some of the slides would be already tweeting out. So, and feel free to ask me questions if you want. Thank you.
Thank you very much. We have about 5 minutes for questions.
For interactivity, like in the JavaScript space, like what have you been seeing in terms of fun technologies that you like to use?
So I think JavaScript base really comes into play when you actually start to do visualization for communication, because they really require you to do a lot of custom visualization or custom code to actually do it, right? So D3 is, again, D3.js is what is used in a lot of cases. There are now abstractions built on top of that which allow you to do that, right? So charting libraries is one way to think about those, but there are also tools which are trying to build this, so replicating Tableau on the web kind of thing. So go and look at basically Vega and kind of the tools set around it, Compass, Voyager, which are trying to look at visualization. Lyra, there are a lot of tools coming out of Jeffrey here's team, and they're looking at how to visualize this interactively large data sets, both to help you choose visualizations as well as to do a lot of Tableau kind of stuff also. So those are kind of interesting things to look at. Raw is another, by density design, is another another tool that you could look at in terms of visualization on the web. But it still largely requires you to do a lot of custom coding. I think that's been the basic challenge. So till more and more abstractions on top of D3 or libraries like this get built, you may still probably need to rely much more on tools on the other end to do exploration. And I'm talking really about exploration. So,
what's the name of the team you said was working on?
Jeffrey here is the teams. Yeah. I mean, the tools to look out for in R would be something like ggviz by Hadley Wickham, or probably in Python, maybe something like Boca. Be the one.
Any other questions?
Sure.
So in visualizing data for exploration, what sort of patterns are you looking out for when you sort of when you plot all these things, especially when it gets to so many dimensions? What sort of patterns are you looking out for?
Yeah, so especially, well, in the lower dimensions, it's like if you're just plotting a scatter, to a large extent, you're really looking for what you would say low correlation, high correlation, outliers, trends, and those kinds, right? The challenge becomes in higher dimensions is really, it's an acquired skill, right? So think of yourself as a radiologist, right? You look at an X-ray and you look at it and you can't understand anything, but a radiologist can look at it. So think of even visual analytics as a way of building your knowledge about how to understand them much better. Especially in higher dimensions, if you go down to kind of tours and projections, it is really an acquired skill that over time you can start to see, how do I lay these multi-graphs together, or how do I look at tours and projections and rotate them. And a lot of automation is also happening around that to help reduce the human cost, because the cost of looking at each graph is the cost that you really have, right? So if I can narrow down that process, so there's a lot of automation still happening in visualization so that they do some amount of selection so that then you are given an option to kind of make those choices. But I think it's a mix of both. So wait for tools to also get better, but also build up your visual literacy on how to understand each of these much better.
Another 3 minutes, so we can take another 2 questions, I think. Maybe I'll ask one. Is the idea here that we take a set of data, put it through a library that explodes into multiple visualizations, and then go through those visualizations and see if there is any interesting patterns? And that last process, could it be, since most of the time visualization patterns is something that's an outlier, could it be something that is machine learning?
Yeah, so yes, I mean, one of the ideas I have is obviously, is that modeling and visualization needs to go hand in hand, right? So a lot of the tools, and even tools that are there out here, people are showcasing, largely go straight down to the modeling. So I'm going to run you all the 30 models that are there, and help you, select from those 30 models. But if you go and talk to any machine learning person, he will tell you about how feature engineering is such an important part. But how do you really do feature engineering without trying to understand your data a little bit, right? So that's where kind of this modeling and exploration needs to go together. And the intention of my talk is really to get people to use that much more, right? So to leave the fear of trying to, I can't do visualization, I can do modeling, great, let me jump straight into it. But no, to go to visualization, build a little better understanding of the data, do much more feature engineering, and your models will improve by that design, right? The second question that you asked really around is kind of the same question. He's saying, yes, there are automated selections that are happening so that this process of winnowing down the number of visualizations that you can look at needs to happen much more, yes, because it's a hard process. If I say there are 20 variables, 20C2 is a large combination set for me to even look 2x2 combinations of each one of them, right? So there has to be some way of some automated selection to say, okay, now I've looked at this data and then I've found some outliers, I've found some interesting trends. This is the ones that I want you to go back and look. And that's where I guess a lot of the people who are designing tools around visualization need to help the user kind of winnow down this process so that their time is being used in a very productive way.
Okay, thank you very much.
Well, thank you.